In the last class, we were talking about how to design a plate girder without using intermediate transverse stiffeners. Technically, we have used the end bearing stiffeners, right? So in the previous problem, if you check down, we have used the end bearing stiffeners, but we haven't used the intermediate transverse stiffeners. But in today's class, the same problem will be there. The data, whichever we have used in the first problem, that is 24 meter span, 100 kilonewtons per meter of uniformly distributed load, everything remains same, but except here in the problem one, we have talked that without intermediate transverse stiffeners, but here we are going to use using intermediate transverse stiffeners. That's the only difference between the problem. Okay, apart from that, the data remains same. So since the data, that is the length and the load parameters are remaining same, the same values of the things, that is whatever we have done in the design forces, okay, so these data doesn't change. Okay, the same data will be there, so you can make the first step as same as problem one or same as model one. You can write this one. So the data remains same, the data doesn't change anything at all. It means the maximum bending moment, the maximum shear forces, they don't change anything at all. And also, as far as the design of web is concerned, okay, the design of the web also doesn't change. That means the dimensions of the design of web also doesn't change. I'll let you know a very small thing gets changed here, but however, the process remains same. You don't, the value of K is considered as 180 only, and then you have to find out the depth of the web, that is economical depth, and then you have to find out the thickness of the web. Okay, and ultimately you got the web plate dimensions as 1800 by 1200 mm, 12 mm. Okay, but here there is a small difference here. I'll talk about this. So the design of the flanges also doesn't change. The same values will remain same, and ultimately the flange dimensions for the second model of problem will also remain same. That is 560 by 50 mm. Okay, so up to here nothing gets changed. Okay, the first step, that is the design forces, the design of web, and the design of flanges. These three steps doesn't change anything at all. Of course, there is some change in the design of web that I'll talk later. So remember, up to here you have to solve. So from classification of flanges, the things get changed. You will get entirely different process from here. Okay, I'll talk about that. So to begin our problem, so I'll write the same data from model 2 problem. Okay, model 1 problem. So I'm just mentioning it as from model 1 problem. That is the previous problem which we have solved in the last class. That is this one. Okay, this is what you can make it as model 1 and this problem as model 2. So from model 1 problem, we are extracting some data. That data is the maximum bending moment, that is M value, which we have obtained as 11,448 kilonewton meter. And we are also extracting the maximum shear force, which is 1908 kilonewtons. Okay, and we'll also be extracting the data of the dimensions of the flange plates. Dimensions of flange. This one. Dimensions of flange, which is 560 mm is the width and 50 mm is the thickness. Okay, now we are also going to extract the dimensions of the web. First, let me write the dimensions of the web which we have adopted. So dimensions of web. So what are the dimensions of the web? Let me check and then I'll write on the things. So the dimensions of the web are 1800 by 12 mm. Okay, so the dimensions of the web are 1800 divided by 12 mm. So I'll highlight this particular portion because this is not the exact value which you have to consider while you are using the intermediate transverse stiffener. So I'm just highlighting this. I'll talk about this, why we are not using the same data of the dimensions of the web in this problem. Now, in order to understand why there is a need to change the dimensions of the web when you are using intermediate transverse stiffeners, you need to understand a few concepts which we have discussed in the first model problem. So remember in the model 1 problem, that is without using intermediate transverse stiffness problem, we have got the depth of the web as 1871.9 mm. That is the original depth of the web, but we have decreased the depth of the web. Okay, so remember you have got the some depth value, and what we have done is we have decreased the depth of the web. And if you look at the thickness of the web thing, so this is one parameter, the other parameter is thickness of the web. So you have got 10.95 mm as the thickness of the web, and what we have done is we have increased the thickness of the web. Remember this thing. This is the concept which is involved here. So in the model 1 problem, whatever the depth that we have got, we have decreased the depth and then we have assumed some depth value. But the thickness of the web, whatever the thickness of the web we have got, that is 10.95 mm, we have increased the thickness of the web and then we have designed the problem. Okay, but in model 2 problem, okay, but in model 2 problem, what we are going to do is we are going to do the exact opposite of this phenomenon. Okay, so we are in model 2 problem, what we are going to do is exact opposite to this phenomenon. That is, we are going to increase the depth of the web. Okay, we are going to increase the depth of the web, and then we are going to decrease the thickness of the web. Remember this thing. This logic is very important to solve model 2 problem. So this applies to model 2 problem. That is when you are using intermediate transverse stiffness. And the first case applies to model 1 problem. That is this one. Okay. Why? What is a need to do the increase or decrease in the depths and the thickness of the webs? It is because since in this problem, that is in model 1 problem, you are not using any intermediate transverse stiffness, right? So in model 1 problem, since you are not using intermediate transverse stiffness, there is a need to increase the thickness of the web. Okay, there is a need to increase the thickness of the web so that the web portion will not get buckled. I'll repeat the statement. In model 1 problem, since we are not using intermediate transverse stiffness, what we have done is we have increased the thickness of the web so that if any extra amount of loads are coming onto the member, this web will not get buckled due to the increased thickness of the web. And also we have decreased the depth of the web, right? We have decreased the depth of the web in model 1 problem because the more the depth of the web, the more will be the chance of the web to get buckled. I'll repeat the statement. The more the depth of the web, the more will be the chance of the web to get buckled. Okay, so that's the reason we have decreased the web depth of the web to avoid buckling, and we have increased the thickness of the web to ensure the safety against buckling. Why we are decreasing the depth of the web and increasing the thickness of the web? It is because we are providing only the end stiffness. It is because we are providing only the end stiffness. But in model 2 problem, if you check this statement, we are increasing the depth of the web and we are decreasing the thickness of the web. Okay, please have a very careful look at here. In model 2 problem, we are increasing the depth of the web and we are decreasing the thickness of the web. The reason for this is in model 2 problems, we are going to provide the intermediate transverse stiffness. Okay, we are going to provide intermediate transverse stiffness. That's what the problem says. Okay, so when you are providing the intermediate transverse stiffness, you can increase the depth of the web. Okay, you can increase the depth of the web because now you might have a question that, sir, if you are increasing the depth of the web, there is a chance that the web portion of the web portion of the plate girder might get buckled. Yes, that will get buckled. But thing is, here we are providing intermediate transverse stiffness. If you are providing intermediate transverse stiffness, that means you are ensuring the safety of the member for buckling. Okay, so that's the reason why we are increasing the depth of the web in the model 2 problem. And why we are decreasing the thickness of the web in model 2 problem is, always remember when you are providing or when you are designing the plate girder using intermediate transverse stiffeners, you should ensure the thickness of the web to be the smaller value. You should ensure the thickness of the web to be the smallest value. Okay, it is because we are going to design the web as a thin web. In model 2 problems, you are designing the web portion as a thin web, which is called as a slender web. Slender is nothing but bending. Okay, you're going to design the web portion as a slender web. So that's the reason why we are increasing the depth of the web and why we are decreasing the thickness of the web in the model 2 problem. Okay, so I hope the concept is clear. So if you clear with this concept, then it is very easy to understand why we are doing this decrease and increase in the thickness of the webs. Okay, anyways, I'll start the process of solving. So as I said earlier, what I am doing in this model 2 problem is I am going to increase the depth of the web from 1800 mm. I'm going to increase it to 2000 mm. And then from 12 mm, I'm going to decrease the thickness of the web to 10 mm. Okay, this is just a condition. Okay, so let me make that changes. So therefore, try 2000 by 10 mm dimensions of web. Dimensions of web. Now you might have a question, but sir, in the exam, suppose now we have the first model problem, so it is easy for us to make a comparison, and then it is easy for us to either increase or decrease the thickness and depths of the web. But in the exam, we have only one problem. So how shall we decide whether to increase or whether to decrease the depth and thicknesses? So it depends on one condition. What is that condition is, first you have to check for the question. Okay, you have to check for the question whether they are asking to design using intermediate transverse stiffeners or to design without using intermediate transverse stiffeners. So if they are letting you tell, so I'll make the note statement here. If in the question, if they say use without intermediate transverse stiffeners, ITS, I'm just writing it as for convenience purpose. So in the question, I mean in the exam, if they ask you design the plate girder without intermediate transverse stiffeners, then automatically whatever the depth that you are getting, okay, whatever the depth that you are getting, you increase, you decrease this web. Okay, suppose say for example you have got the web dimension depth as 2000. So you decrease this value to 1800 or 1900 mm. Okay, that's what you have to do. And whatever the thickness of the web you are obtaining, you increase the thickness of the web. Suppose say for example you have got the thickness of the web as 12.5 mm. Okay, so therefore here you take it as 14 mm. This is applicable for first model, that is when you are not using intermediate transverse stiffeners. Suppose if the problem is asked use intermediate transverse stiffeners or provide intermediate transverse stiffeners, if this is the case, then whatever the depth that you are obtaining, you increase the depth of the web. Suppose say for example you have got the depth of the web as 2100 mm. So you increase this depth to 2200 or 2300 mm. Maybe plus or minus 200 is sufficient. Don't go more than that. Okay, and whatever the thickness of the web you are obtaining, you decrease the thickness of the web by plus or minus 2 mm. Okay, suppose say for example you have got the thickness of the web as 12 mm. So plus or minus 2 mm is sufficient. You decrease the thickness of the web to 10 mm. So remember these conditions, plus or minus 2, and here plus or minus 200. Sorry, 200 it is. Okay, remember these conditions. So here also it is the same. So plus or minus 200 mm you can increase or decrease, and plus or minus 2 mm you can increase or decrease. Remember these conditions. These are very important. Okay, so from this I'm just trying some dimensions, that is try 2000 by 10 mm dimensions of the web. That means here the depth of the web is 2000 and thickness of the web is 10 mm. That's how you're going to fix the dimensions of the web. Okay. Anyways, but remember the first three steps which we have solved there, those steps has to be solved in this problem also. Okay, don't directly write from model 1 problem we are extracting this data. It is not possible also because you have to solve in the exam. Okay, so anyways, from the next step I'm going to continue. Okay, you can make this as the fourth step, because first three steps we have solved. The first step is design forces. I'll write with another color. The first step is design forces, and the second step is design of web. Okay, and the third step is design of flange. Okay, so these three steps are mandatory for this problem also. So I'm directly solving from the fourth step. So here the fourth step gets changed. Okay, so what you're going to do is you're going to design the intermediate transverse stiffeners. Okay, so let's write that statement. The requirement of intermediate transverse stiffeners. Requirement of intermediate transverse stiffeners, because we are providing the intermediate transverse stiffeners. So for this purpose, we are going to solve this additional step, which is requirement of intermediate transverse stiffeners. Now, how will you solve this step? This step has a little different process. So in order to solve the requirement of the intermediate transverse stiffeners, initially you have to assume one thing. That is, let us assume the ratio of spacing of the stiffeners, that is C, to depth of web, that is D, equals to 1.4. Remember this thing. So let us assume the ratio of C by D equals to 1.4, where C is the spacing of stiffeners. This is fixed value. We are just assuming this. And D is the depth of web, or economical depth, anything is same. Okay, so therefore spacing of intermediate transverse stiffeners equals to spacing of intermediate transverse stiffeners. Spacing of intermediate transverse stiffeners is denoted with C equals to 1.4 times of depth of the web. What is the depth of the web? We have assumed the depth of the web as 2000. So 2000. So how does this 1.4 is coming? It is coming from this logic, that is C by D equals to 1.4. So I'm finding from this equation, I'm finding the value of C. That's how 1.4 into 2000 has come. So therefore spacing equals to 2800 mm, because spacing equals to 2800 mm. So this should be the spacing between any two intermediate stiffeners. Okay, suppose if you are considering this as the entire portion of the web, and here you are providing the end stiffeners, and you have to provide the intermediate stiffeners now. So if you are providing the intermediate stiffeners, the spacing between two intermediate stiffeners will be 2800 mm. That is almost 2.8 meters. Okay, but there is a small revision for this. I'll talk about the revision later. So this is how you're going to provide the spacing of the stiffeners. Let me wait. Yeah. So now you have got the spacing of the stiffeners or intermediate stiffeners. And we shall also have to find the value of D by TW. Remember, we also have to find out the value of D by TW, where D is the depth of the web and TW is the thickness of the web, which will be 200. Okay. Now, if you remember the conditions of from serviceability criteria, okay, we have discussed that in the previous problem also. From serviceability criteria, okay, from serviceability criteria, when 3D is greater than or equals to C, greater than or equals to D. This is the condition. When 3D is greater than or equals to C and greater than or equals to D, the value of D by TW, okay, the value of D by TW must be less than or equals to 200. Okay, so from serviceability condition, when you are providing intermediate transverse stiffness, this condition has to be get satisfied. That is, D by TW value must be less than or equals to 200. So here the value of D by TW is 200. So this condition is getting satisfied. Okay, so hence safe. Okay, I hope it is clear for all of you. Now there is an additional thing which you have to do. So here what you have to do is, when you are providing intermediate transverse stiffness, you need to find out how many panels are going to form, right? So I have said in the diagram, so these are the end stiffness, and if you are providing the intermediate stiffness, okay, so you have to find out how many panels are getting formed. So this is panel 1, panel 2, panel 3, panel 4, panel 5, likewise how many panels are coming. So you have to find out the number of panels now. Okay, so I'll solve how to find out, I'll let you know how to find out the number of panels. So number of panels formed by stiffness equals to number of panels formed by stiffness. Okay, number of panels formed by stiffness equals to length of girder, okay, length of girder divided by spacing of girder, spacing of the transverse stiffness. What is the length of the girder? If you check the question, the length of the girder is 24 meters. So I'm making it as 24,000 mm. And the spacing of the girder is 2,800. You can see here 2,800. So therefore 2,800. So if you solve for this one, it will be getting us 8.57. So approximately 9 panels are required, or 9 panels are getting formed. Okay, so why we are calculating for number of panels? Because you are providing the intermediate transverse stiffness. When you are providing the intermediate transverse stiffness, you should also know how many panels that are getting formed. So if you know the number of panels, then it will become easy for the calculation purpose. Now let's calculate what is the actual spacing of the stiffness based on panels. Actual spacing of stiffness. Now we know the number of panels, that is 9. So you need to calculate what is the actual spacing of the stiffness based on the number of panels that are formed. So that is calculated as L, that is the length of the girder, which is 2,400 into, sorry, it is 24,000 upon number of panels, that is 9. So 9 is the number of panels, that equals to 2,666.66 mm. Okay, so now this should be the spacing between the stiffness. Okay, it is not 2,800. Okay, it is not this value. Up to this much you can provide, but the optimum thickness, optimum spacing will be, if you provide 2,666 mm, that will be sufficient to take care of the loads or to take care of the bending moment and shear forces. Okay, so that's how you're going to calculate the actual spacing of the stiffness. Now here you have to find out the value of C by D. Okay, you need to find out the value of C by D. So let C by D equals to, what is the C value? It is the spacing of the stiffness. What is this? It is 2,666.66 mm. So 2,666.66, that is the spacing. Don't take it as 2,800. So 2,666 is the one which we are providing to our connection. Okay, it is not 2,800. So what is the depth? It is the value of depth of the web. So what is the depth of the web? we have assumed it to 2000 mm. So I'm taking it as 2000. So if you solve for this one, you will be getting the C by D ratio as 1.33. So if you want, you can check down. So if you calculate the value of C by D, it is 1.33. Now, I want you to open, not open, but just understand when C by D ratio, okay, when C by D ratio is less than 1.5. So we have got the C by D ratio as 1.33, which is less than 1.5. So when C by D ratio is less than 1.5, remember the value of D by TW must be less than or equals to 345. Okay, when C by D ratio is less than 1.5, the value of D by TW must also be less than or equals to 345. So we know that ratio of D by TW value, which is 200. So 200 is less than 345. So both the conditions are getting satisfied. So now there is a requirement to provide the intermediate transverse stiffeners. So that's how you're going to find out whether there is a requirement of intermediate transverse stiffeners or not. Okay, so therefore intermediate transverse stiffeners are to be provided. Okay, we know actually in the beginning of the problem only we know where we have to provide intermediate transverse stiffener, but we are just checking is there a real requirement or not, that we are checking. So in order to check that, we have to do this process. Okay, so in the next step we are going to solve for the shear capacity of web. So the fifth step is shear capacity of web, same as the previous problem but with a little change. Shear capacity of web. Now here I want you to open page number 60 of IS 800 2007. So if you open page number 60 of IS 800 2007, what you're going to find out is you need to find out the value of elastic critical shear stress, and you're also going to find out the value of VCR. So if you have opened page 60 of IS 800 2007, okay, that is clause 8.4.2.2. Okay, so now here in order to find out the shear capacity of the web, in the question they have said that use post critical method. So based on this you are going to find out the shear capacity of the web. Suppose if they ask you to use the other method, okay, then you have to go with the other process, that is tension field method. So since in the problem they have said use post critical method, so you in the shear capacity of the web you have to use the simple post critical method. So using simple post critical method. Okay, so that's how you're going to refer clause 8.4.2.2 of page 60. So here you need to find out the value of VCR, you need to find out the value of lambda W, then tau CRE, which is elastic critical shear stress. So let's find out all these values. Now let's come from the bottom, that is let's try solving for the value of tau CRE. So tau CRE is called as elastic critical shear stress. So you need to write the complete statement. Elastic critical shear stress, that equals to kV into pi square E upon 12 into 1 minus nu square into D by TW whole square. So this formula is there in page 60 of IS 800 2007. You can refer. Both methods are there. Simple post and tension field methods are available in page 60. If you refer that, you will understand. Now here in the previous problem, that is in without using intermediate transverse stiffeners, the value of kV is taken as a 5.35. Okay, so here you can check the value of kV is taken as 5.35. Why we have taken it is because we are not providing the intermediate transverse stiffness. So when you are not providing the intermediate transverse stiffness, you can directly take the value of kV as 5.35. But in our case, that is in the second case, we are using intermediate transverse stiffness. So when you are using intermediate transverse stiffness, okay, when you're using intermediate transverse stiffness, the value of kV depends on C by D ratio. You can refer the code book. So the value of kV depends on C by D ratio. So you have two conditions there. So when C by D ratio is less than 1 and C by D ratio is greater than or equals to 1. Okay, now which one you're going to use? Now here, in our case, the value of C by D is 1.33. So we have solved for this one. The ratio of C by D is 1.33. So we are going to find out for C by D ratio is greater than 1, we have to find out the value of kV. Since C by D is greater than 1, okay, since C by D is greater than 1, kV equals to, you have a formula there, you can look at this, 5.35 plus 4 divided by C by D whole square. 5.35 plus 4 divided by C by D whole square. This is the formula when you have the ratio of C by D greater than or equals to 1. Okay, we have got the C by D as 1.33, which is greater than 1. So from this, you are going to find out the value of kV. So therefore, kV equals to 5.35 plus 4 divided by C is the spacing of the stiffness, which is 2666.66 divided by what is the depth of the web? We have increased the depth of the web to 2000 square. So if you solve for this one, the value of kV is obtained as 7.6. So therefore, substitute all these values in tau CRE in order to get the elastic critical shear stress. So tau CRE equals to kV, that is 7.6 into pi square into E, where E is the Young's modulus of steel, which is 2 into 10 power 5, divided by 12 into 1 minus nu square, where nu is the Poisson's ratio, which is taken as 0.3, and D is the depth, which is 2000 by thickness of the web is 10 square. So if you solve for this one, you will be getting the elastic critical shear stress as 34.34 newtons per mm square. Okay, so from this, you are going to find out the lambda W value. So let lambda W is greater than 1.2. We are just assuming, let us assume this lambda W is greater than 1.2. So when lambda W is greater than 1.2, you have a formula which is slenderness ratio lambda W equals to under root Fy by root 3 into tau CRE. Okay, so you can substitute the values of Fy is 250, root 3 times of tau CRE is 34.34. Okay, so if you solve for this one, the value of slenderness ratio is 2.05, which is greater than 1.2. Okay, we have assumed that lambda W value should be greater than 1.2. So however, we have got 2.05, which is greater than 1.2. So you don't have any confusions here. So when lambda W is greater than 1.2, shear stress corresponding to buckling. Okay, shear stress corresponding to buckling for lambda W greater than 1.2. So the formula is tau B equals to Fy by root 3 into lambda W square. So the value of Fy is 250 by root 3 into lambda W square, which is 2.05 square. So if you solve for this one, the value of tau B, which is shear stress corresponding to buckling, is obtained as 34.345 newtons per mm square. Okay. Now we also have to find out the shear force corresponding to web buckling. Okay. So VCR, which is, so shear force, don't confuse between shear stress and shear force. They are completely different from each other. So shear force corresponding to web buckling, that is VCR. You can check the formula in page 60. You have the formula VCR equals to AV into tau B. That is what that represents, where AV is the area of the web. Okay, AV is called as area of the web. Sometimes you can write as AW also, which is area of the web. So VCR equals to area of the web is obtained from depth into thickness of the web into tau B. So the depth of the web is 2000 and the thickness of the web is 10 into tau B value is 34.345. So if you solve for this one, you will be getting the value as 686.9 kilonewtons. And remember, this value must be less than 1908 kilonewtons. So if VCR is less than V, okay, if VCR is less than V, intermediate transverse stiffeners are required, or provide intermediate transverse stiffeners. If VCR is less than V, intermediate transverse stiffeners are to be provided. Now let's look at what we have done in the previous model problem. So in the previous model problem, we are not using the intermediate transverse stiffeners, but what we have got is initially VCR value, that is 962.2, is less than 1902.08 kilonewtons. So I have set this node parameters also. So if you are not using intermediate transverse stiffeners, if the value of VCR is less than V, then it is considered as an unsafe. Remember, this unsafe condition is applicable only when you are not providing the intermediate transverse stiffeners. But if you are providing the intermediate transverse stiffeners, if you get the value of VCR less than V, that means it is a safe condition, and hence you have to provide the intermediate transverse stiffeners. That's from this case I'm talking about. Okay, so since VCR is less than V, intermediate transverse stiffeners are to be provided. Okay, so the next step has to be solved, which is for end panel design. End panel design. So how will you solve for end panel? This is an additional step we have to solve. So end panel design. So how do you solve for end panel design? Is here you have to find out the longitudinal shear force and also the plastic shear force under pure shear conditions. Okay, I'll talk about how to solve for this one. So longitudinal shear, you have the formula for this. Longitudinal shear, that means the shear which is coming in the longitudinal direction. HQ equals to, you have the formula, that is 1.25 into VP into 1 minus VCR by VP whole power 0.5. This is the fixed formula. Okay, longitudinal shear HQ equals to 1.25 VP into 1 minus VCR by VP whole power 0.5. Now, how will you find out VP value? So here VP is plastic shear resistance. VP is called as plastic shear resistance under pure shear. Under pure shear, that is where bending moment is 0. Okay, so VP value has to be calculated by using this formula, that is VP equals to depth into thickness of the web into Fy divided by √3. This is the fixed formula. Okay, that equals to the value of depth is 2000 and the thickness of the web is 10 into 250 upon √3. Okay, so if you solve for this one, you will be getting the value of Vp as 2886.75 kilonewtons. So therefore, the value of VCR we have obtained from the previous step, which is VCR equals to 686.9 kilonewtons. So now let's just substitute the values in this equation, that is HQ equation. So HQ equals to, you know the formula, that is 1.25 into Vp, where Vp is 2886.75 into 1 minus VCR, which is 686.9 divided by divided by Vp, which is 2886.75 whole power 0.5. So which will be 3150 kilonewtons of load. So the horizontal shear or the longitudinal shear is 3150 kilonewtons. Now let's find out the resultant longitudinal shear. So resultant longitudinal shear. So the resultant longitudinal shear is denoted with RTF equals to, it will be half of HQ. It is HQ divided by 2. So which will be 3150 divided by 2, which will be 1575 kilonewtons. Okay. So this is how you are going to find out the longitudinal shear and also the resultant longitudinal shear. Now let's find out the design shear strength. Design shear strength, which is denoted with VD, that equals to area of the web, that is depth into thickness of the web into Fy divided by √3 into gamma m naught. So where depth and the thickness of the web is, depth of the web is 2000 and thickness of the web is 10 into 250 upon √3 into gamma m naught is taken as 1.1, which is partial safety factor of material, which you get as 2624.32 kilonewtons. 2624.32 kilonewtons. And remember, this value must be greater than the value of resultant longitudinal shear force. So this value must be greater than the resultant longitudinal shear force, that is RTF. So what is the value of RTF? It is 1575. So 2624 is greater than 1575. Therefore, the end panel is safe to carry the forces. So therefore, the end panel is safe to carry the forces. Suppose, say for example, if this condition is not getting satisfied, that is 2624 is less than RTF, then again you have to decrease the thickness of the web, increase the thickness of the, not increase, you have to increase the depth of the web and you still have to decrease the thickness of the web. Okay, alternate arrangements has to be done if the conditions are not getting satisfied. So this is how you are going to check the end panel design. So next, in the 7th step, we are going to find out the moment capacity of end panel. So keep the heading as check for moment capacity of end panel. Check for moment capacity of end panel. So how do you find out the moment value? So moment MTF equals to, you have a formula for this, which is HQ into D divided by 10. where HQ is the horizontal shear, that is 3150, which we have got, and D is the depth of the web, which is 2000 divided by 10. So if you solve for this one, you will be getting the moment value as 630 kilonewtons meter. Okay, and you also have to find out the moment of resistance, which is MQ, moment of resistance, which is MQ, equals to I by Y into Fy by gamma m naught. I by Y into Fy by gamma m naught, where Y is taken as half of the spacing of stiffness. Y is taken as half of spacing of stiffness. The value of spacing of stiffness is 2,666.66 divided by 2, which will give you 1,333.3 mm. Okay, and the value of moment of inertia, that is I, is taken as thickness of web into spacing cube divided by 12. Thickness of the web into spacing cube divided by 12. So you know the thickness of the web, which is 10, and the spacing value is 2,666.66 cube divided by 12. So that is BD cube by 12 concept. So which will be 15802.3 into 10 power 6 mm power 4. Okay, so and finally you have to find out the value of MQ. So therefore MQ equals to, just substitute the values in the above formula, which is MQ formula is I by Y, where I is 15802.3 into 10 power 6, and Y value is 1,333.33 into Fy by gamma m naught, where Fy is 250 and gamma m naught is 1.1. So if you solve for this one, you will be getting as 2693.58 kilonewtons meter. And remember, this value must be greater than the value of MTF. Okay, so you have got the value of MTF as 630 kilonewtons meter. So 2693 kilonewtons per meter is greater than 630 kilonewtons meter. So therefore, it is safe, and therefore it is safe. Hence, the end panel can also carry the moments. So I'll write the statement here. The end panel is safe to carry the moments. Is safe to carry the moment or moments. Okay, so in the next step, we are going to solve for design of end bearing stiffeners. Remember, it is not that you are just how to design the intermediate stiffeners. If you are providing intermediate stiffeners, you also have to provide the end. You also have to provide the intermediate end bearing stiffeners. So in order to provide end bearing stiffeners, so you need, I'll just write the step, design of end bearing stiffener. Design of end bearing stiffener. So you have to find out this value, or you have to design actually. So that is designed as force due to, okay, force due to moment. Force due to moment. FTF equals to MTF, okay, that is the moment value divided by spacing of the stiffener. So the moment value, that is MTF value, we have solved in the previous step, that is 630 kilonewtons meter. So 630 kilonewtons meter divided by spacing is 2,666.66. If you solve for this one, you will be getting as 236.25 kilonewtons. Or you can make it here as 10 cube. Okay, so this is the force due to moment. Now you need to find out the total compressive force that is coming on the end bearing. Total compressive force, that is FC equals to the maximum shear, that is capital V value. So here you need to find out the values of total compressive force. So the total compressive force is actually the summation of the maximum shear force plus force due to moment. The maximum shear force is 1908, which we have calculated in the very first steps of the previous problem. And FTF is force due to moment, which is 236.25. Okay, so if you solve for this one, you will be getting the total answer, the total compressive force as 2144.25 kilonewtons. 2144.25 kilonewtons. Now you need to find out the area of the stiffener, right? You need to know the size, width, and the thickness of the stiffener, right? So in order to find out that, you need to have the value of area. So required area of stiffener, AQ, Q is nothing but stiffener, you can say, or AQ is nothing but area of stiffener. Area of the stiffener must be greater than 0.8 into FC into gamma m0 upon F5. Okay, so let's solve for this one. AQ value must be greater than 0.8 into FC, which is total compressive force, that is 2144.25 into gamma m0 is 1.1 divided by F5, which is 250. So this is 7547.76 mm square. Okay, so if you are providing the stiffener dimensions, those stiffener dimensions should have an area greater than 7547 mm square. So that's the condition. So now here the question is, you know only the area of the stiffeners. You have to find out what should be the width of the stiffener and what should be the thickness of the stiffener. You don't know these two parameters. You only know the area. Now what you have to do is, it's a trial and error method. You have to randomly select the width and the thickness of the stiffener, and then you have to verify whether the specified dimensions or whether the dimensions which you have selected is giving an area greater than 7547 or not. Suppose, say for example, I am taking the width of the stiffener. It is just a trial and error method. So I'm just making it as trial 1. So in trial 1, I'm just taking the width as 100 and depth as thickness as 20. So it will give you 2000 mm square, so which is not sufficient. In trial 2, I am just taking it as 120 into the thickness of the web. Maybe I'm increasing it to 30. So then it will give you 36,000 mm square. Okay, it is giving you 36,000 mm square. So which is also not in the safe zone. Now the thing is here, this trial and error method has to be go on till this condition is getting satisfied, that is 7547 is getting satisfied. Now the thing is here, the stiffeners are provided on either side of the web. Remember this thing. So the stiffeners are to be provided on either side of the web. So let's write that statement. So the stiffeners are provided on either side of. Okay, now the thing is, how will you specify the dimensions of the stiffeners? So let us try. Okay, let us try. It is just a trial and error method. So after doing trial and error method, so I'm just trying to Okay, we are providing the stiffness on either sides of the web. So that is what 2 is. 2 stiffness of dimensions 190 of width and 20 mm of thickness. Okay, so 190 is the width, ISF represents Indian standard flat, and 20 is the thickness of the flat section, that is the stiffener section. As stiffener, one on each side of web. Okay, so therefore total area provided, that is AQ, equals to, you are providing 2 stiffeners, okay, one on each side, into 190 into 20, that is area of one stiffener, so which will be 7600 mm square. And remember, what is our condition? So the area of the stiffeners must be greater than 7547.76 mm square, okay, which is a required area. So the area which you have provided is 7600, and the area which is required is 7547, which is safe. Okay, so it is just a trial and error method. So you